Welcome to today's Explainer. We're diving straight into something absolutely mind-blowing today. The invisible backbone of literally our entire modern world, electromagnetic waves. I mean, think about it. Without these guys, there's no internet, no smartphones, and no modern medicine. So let's uncover the invisible physics powering practically everything we do. Let me ask you this. How exactly does your TV remote change the channel without a wire? We all just kind of take it for granted, right? But instantaneously, real energy leaps across empty space just to trigger a reaction in your television. And that seemingly magical, invisible transfer of energy, well, that is exactly what we're decoding today. So here is our game plan for this explainer. First, what actually is an EM wave? Second, their unique properties. Third, the math and the sheer speed behind them. Fourth, the electromagnetic spectrum. And finally, we'll wrap up by solving a real problem together. All right, Section 1. What is an EM wave? The origin story. Let's build right on what we already know about alternating currents and transformers. It really all starts with a fascinating chain reaction. Step 1. An alternating current flows through a wire or conductor. Now, because that current is alternating, it's actively moving back and forth, it triggers Step 2, which is where the surrounding electric and magnetic fields start to fluctuate. And then boom! That specific fluctuation gives birth to Step 3. An electromagnetic wave is generated and just radiates outward into space. So if we want the strict academic definition here, an electromagnetic wave is a wave consisting of vibrating, mutually perpendicular electric and magnetic fields that travels and, most importantly, carries energy. Just try to picture two waves traveling forward together. One is waving up and down, the other is waving side to side. They are at exact right angles to each other, carrying actual, measurable energy across space. It's like a perfectly choreographed dance. Moving right along to Section 2, unique properties. What makes EM waves so special? Well, quite a bit, actually. First off, they're transverse waves, meaning they oscillate perpendicular to the direction they're traveling. But here's the absolute kicker. They can travel in a perfect vacuum. They need absolutely no physical medium whatsoever to move. No air, no water, nothing. That's how sunlight actually reaches us across the complete emptiness of deep space. Plus, of course, they still carry energy and experience all the classic wave behaviors. You know, reflection, refraction, interference, diffraction, and polarization. The whole shebang. Okay, Section 3. The math in speed. Calculating the invisible. And don't worry, the formulas here are really just tools to help us understand reality. Get this, the speed of an electromagnetic wave in a vacuum, which is the speed of light, represented by the letter c, is a staggering 3 × 10 to the 8th power meters per second. Put simply, that is 300 million meters every single second. That is literally the ultimate speed limit of the entire universe. No way around it. Now, because that speed of light is an unbreakable constant, it creates a strict inverse relationship between a wave's frequency, f, and its wavelength, which we call lambda. It's all tied together by a beautifully simple formula, c equals f times lambda. This means as frequency goes up, wavelength absolutely must go down. And vice versa. They are eternally locked in this cosmic balancing act. Which brings us nicely to Section 4, the electromagnetic spectrum, the scale of energy. Let's climb the ladder. This spectrum is where all that abstract physics suddenly becomes our daily lives. At the low-energy, long wavelength end, we've got radio and microwaves. That's your communications, your Wi-Fi, your radar. Bumping up the energy scale, we hit infrared. That's your TV remote and thermal imaging. And then visible light. Yeah, all the colors we actually see are just a tiny narrow band on this massive spectrum. Go further up, and ultraviolet sterilizes things, while X-rays have enough energy to pass right through human tissue for medical imaging. Finally, at the absolute highest frequencies and shortest wavelengths, we have gamma rays, which literally pack enough punch to target and destroy cancer cells. But remember, a gamma ray and a Wi-Fi signal, it's the exact same fundamental physics, just scaled way up. Let's test this out. Section 5. Solving a problem. Applying the physics. Time for a quick puzzle. Imagine we have an electromagnetic wave with a frequency of 100 megahertz. We know our constant, the speed of light, is 3 × 10 to the 8th meters per second. So our goal here is simple. What is the wavelength? Let's crack this. Using that master formula we talked about, we just rearrange it to solve for wavelength. So lambda equals c divided by f. We plug in our cosmic speed limit, 300 million meters per second, and divide it by our frequency of 100 million hertz. And the result? A clean, perfect 3 meters. Think about that for a second. When you tune into a 100 megahertz radio station in your car, your antenna is quite literally pulling 3-meter-long, invisible waves right out of the air. How cool is that?
All right, let's bring it all home and summarize our main takeaways. Electromagnetic waves cross the freezing vacuum of space effortlessly, needing zero physical medium. They exist across a truly vast spectrum of frequencies, all the way from building-sized radio waves down to subatomic gamma rays. And most importantly, they serve as the undeniable, invisible foundation for almost all modern technology.
So here is a quick practice exercise for you. Look around the room you're sitting in right now. What everyday applications of electromagnetic waves can you spot? Is it the Wi-Fi router blinking in the corner, the sunlight streaming through the window, or hey, the cell phone you might be holding? They're everywhere. And it really makes you wonder, as we keep harnessing higher and higher frequencies of this invisible spectrum, what kind of wild technologies are going to become possible in the next 10 years? Keep questioning the invisible world around you, and thanks so much for joining me on this explainer.